Welcome back to Fusion Facts. Cosmic Radiance, Solar Mysteries, and the Miyake Enigma. The Extreme Solar Particle Event, ESP, a deep dive into solar phenomena. The universe, with its vast expanse and myriad celestial wonders, has always been a subject of profound curiosity and study. Among its many marvels, our sun, a seemingly constant beacon in the sky, is a hub of dynamic activities and mysteries. One such enigmatic phenomenon that has captured the attention of scientists and researchers worldwide is the Extreme Solar Particle Event, SPE. This video delves into the intricacies of SPs, exploring their origins, implications, and significance in the broader context of solar and cosmic events. Origins and characteristics of ESPs. At its core, the Sun is a thermonuclear furnace, continuously undergoing nuclear fusion. This process not only bestows the Sun with its luminosity, but also results in the ejection of a myriad of particles, collectively known as solar wind. Occasionally, this seemingly gentle breeze of particles is interspersed with bursts of high-energy particles, leading to what we term solar particle events, SPEs. These particles, predominantly protons, can sometimes possess energies that surpass several billion electron volts, marking the event as extreme. ESPEs are characterized by their sheer intensity and the rapidity with which they occur. Unlike regular solar flares or coronal mass ejections, which can be anticipated to some extent due to visible changes on the Sun's surface, ESPs often strike without much forewarning. Their origins are still a subject of research, but it's believed that they are the result of complex interactions between solar flares, magnetic fields, and other solar phenomena. Historical evidence and discoveries. The study of SPs is not just confined to modern scientific instruments. Nature, in its own intricate way, has recorded these events for millennia. One of the most compelling pieces of evidence comes from natural archives like ice cores and tree rings. These natural record keepers, through the presence of cosmogenic radionuclides, provide a glimpse into past ESPs. For instance, a significant ESP that occurred roughly 9,200 years ago was identified through the study of these radionuclides. Such discoveries offer invaluable insights into the frequency, intensity, and patterns of past ESPs, allowing scientists to draw parallels and make predictions about future events. Implications for Earth and its inhabitants. The Earth, with its protective magnetosphere and atmosphere, acts as a shield against most of the Sun's emissions. However, ESPs, with their high energy, can penetrate these defenses to some extent. When these charged particles interact with the Earth's magnetosphere, they can induce geomagnetic storms. Such storms can have a range of effects, from creating vivid auroras in the polar skies to disrupting satellite communications and power grids. Furthermore, ESPs can also pose a radiation hazard, especially for astronauts in space or for air travel routes that pass close to the polar regions. The increased radiation levels during an ESP can interfere with satellite electronics, potentially leading to malfunctions or complete failures. The future of SP research. As our reliance on technology grows, understanding and predicting SPs becomes paramount. Modern space missions, satellite networks, and even some terrestrial technologies are vulnerable to the effects of SPs. Recognizing this, there has been a surge in research aimed at understanding the origins, patterns, and potential triggers of SPs. Advanced solar observatories, both terrestrial and space-based, are continuously monitoring the Sun for any signs of unusual activity. In tandem with observational data, computational models are being developed to simulate and predict SPs. These models, although in their nascent stages, hold the promise of providing early warnings, allowing for necessary precautions to be taken. The Miyake Event, unraveling a radiocarbon mystery. In the vast tapestry of cosmic and solar events, certain phenomena stand out, not just for their scientific significance, but also for the mysteries they encapsulate. The Miyake Event, a sudden and significant spike in radiocarbon levels detected in tree rings, is one such enigma that has intrigued and puzzled researchers for years. Next, let's delve into the intricacies of the Miyake Event, exploring its discovery, implications, and the ongoing quest to understand its origins. Discovery and initial observations. The Miyake Event is named after Dr. Fusa Miyake, a Japanese scientist whose meticulous research in dendrochronology led to its identification. By analyzing the annual growth rings of trees, which serve as natural chronicles of environmental conditions, Dr. Miyake and her team identified significant spikes in radiocarbon levels from the years 774 and 993 AD. These spikes, which were consistent across various tree samples from different regions, indicated a sudden and intense burst of cosmic radiation that affected the Earth. Potential origins and theories. The immediate question that arose following the discovery of the Miyake Event was its origin. What could cause such a significant and global surge in radiocarbon levels? Several theories were proposed, each with its own set of supporting evidence and challenges. Solar flares. One of the initial theories was that massive solar flares, intense bursts of radiation emanating from the sun, were responsible for the radiocarbon spikes. Solar flares, known to increase the levels of cosmic radiation reaching the Earth, seemed a plausible explanation. However, the intensity and global reach of the Miyake events suggested an event much more powerful than typical solar flares. Supernovae. Another theory proposed that the radiocarbon spikes were the result of a nearby supernova explosion. Supernovae, the explosive deaths of massive stars, release vast amounts of energy and cosmic radiation. However, there was no historical or astronomical evidence of a visible supernova during the years corresponding to the Miyake events. Gamma-ray bursts. Some researchers suggested that gamma-ray bursts, extremely energetic explosions from distant galaxies, might be the culprits. These bursts, though rare, can release more energy in a few seconds than the sun will in its entire lifetime. Implications and significance. The Miyake event is not just a historical or astronomical curiosity. It has profound implications for various fields of study. For climatologists and environmental scientists, understanding such events is crucial for reconstructing past climatic conditions and predicting future anomalies. The spikes in radiocarbon levels can also serve as chronological markers, assisting archaeologists and historians in dating ancient artifacts and events. Furthermore, the Miyake event underscores the Earth's vulnerability to cosmic events. While our planet's magnetosphere and atmosphere offer protection against most cosmic and solar radiation, intense events like the Miyake can penetrate these defenses, potentially affecting climatic conditions and even posing radiation hazards. The modern-day implications of a Miyake event, navigating a technological era. In the annals of cosmic phenomena, the Miyake event stands as a testament to the unpredictable nature of the universe and its profound impact on Earth. This event indicates a sudden and intense burst of cosmic radiation. But what would happen if a Miyake-like event were to occur in today's technologically advanced world? Technological vulnerabilities. Satellite disruptions. Our modern world is heavily reliant on satellites for communication, navigation, and observation. A surge in cosmic radiation, akin to the Miyake event, could interfere with satellite electronics, potentially leading to malfunctions or complete failures. This disruption could impact everything from GPS systems and satellite television to weather forecasting and scientific research. Power grid failures. The Earth's magnetosphere, which usually protects us from solar and cosmic radiation, could experience fluctuations during an intense radiation event. These fluctuations could induce electric currents in power lines, potentially damaging transformers and causing widespread power outages. Such a scenario would have cascading effects, disrupting daily life, affecting emergency services, and causing economic losses. Data corruption. Our digital age thrives on data. Servers, cloud systems, and personal devices store vast amounts of information. An intense burst of cosmic radiation could potentially corrupt this data, affecting everything from financial transactions to personal records. Health and environmental concerns. While the Earth's atmosphere offers a protective shield against most cosmic radiation, an event of Miyake's magnitude could increase radiation levels, especially in the upper atmosphere. This could pose risks for air travel. High-altitude flights, especially those near the polar regions, could be exposed to elevated radiation levels. This could pose health risks for passengers and crew and might necessitate rerouting of flights. Space missions. Astronauts on space missions, whether aboard the International Space Station or on exploratory missions, would be at significant risk. Space agencies would need to implement protective measures, possibly even aborting missions or hastening returns. Environmental impact. Increased radiation could affect the Earth's ozone layer, leading to its depletion. This could result in higher UV radiation levels reaching the Earth's surface, with potential consequences for ecosystems and human health. Preparedness and response. Anticipating a Miyake-like event in our modern era underscores the importance of preparedness. This includes early warning systems, investing in advanced solar observatories and radiation monitoring systems to detect and predict intense cosmic radiation events. Infrastructure shielding, enhancing the shielding of satellites, power grids, and data centers to minimize the impact of radiation. Public awareness, educating the public about the potential risks and safety measures during such events. As we continue to unravel the mysteries of our cosmos, events like these remind us of the dynamic and ever-evolving nature of the universe. They challenge our perceptions, push the boundaries of our knowledge, and inspire us to look deeper, always seeking to understand the forces that shape our existence. In the vast tapestry of cosmic events, the extreme solar particle events and the Miyake event are but two threads. Yet, they offer invaluable insights into the intricate dance of celestial bodies and the forces that govern them. As we stand on the cusp of new discoveries, one thing remains certain: the universe, with all its wonders and mysteries, will never cease to amaze us. Thank you for watching. Until next time.